This lecture is going to cover the topic of enthalpy of formation. This is one of the methods we can use to determine the enthalpy of a reaction. We've previously covered measurement and calorimetry. And in this case, we're going to be able to look up values and use those to calculate the enthalpy of a reaction. And this will be our first way to sort of predict what will the change in energy be for a chemical reaction that we haven't run. Some sort of definitions first. When we think about a standard enthalpy of formation, so shown here is the symbol of a standard enthalpy of formation. The first thing you see is a delta, so this is a change in enthalpy. We can actually only measure changes in enthalpy. We can't measure an absolute enthalpy of anything. Then we see a degree symbol or a not symbol, so this tells us that it's at standard conditions. And finally, this subscript F tells us that it's the enthalpy of formation. So the definition of an enthalpy of formation is the enthalpy change when 1 mole of a compound is formed at standard conditions, 1 atmosphere of pressure, 298 Kelvin, from elements in their standard state. So a lot to unpack there. The first thing we should take note of is these values, these delta H of formation values, we can look up. So they're in the appendix of most general chemistry textbooks. Your OpenStax textbooks has one. On exams or quizzes, you'd be given a table with these values. All right. The other thing to take note of is the enthalpy of an element in the standard state is defined to be 0. So the first thing we have to ask ourselves is, what does this mean? What is the standard state of a substance? And what we mean by that is, first we have to talk about something called allotropes. We've mentioned this previously, but remember, an allotrope are compounds that have different structures of the same element. So these are compounds that are all made of the same singular element. So diamonds, graphites, and Buckminster fullerene are all made of carbon and only carbon. So they're allotropes of each other. They're just different forms where the bonding between carbon atoms is different in each of these, and that's going to give rise to different properties. So the standard state of a substance will be the lowest energy state of that element. So there's multiple kinds of carbon. We just looked at 3 forms of it. So the lowest energy form is the standard state of carbon. And if we were to look at it on an enthalpy diagram, enthalpy on the y-axis, we see that graphite is the most stable form of carbon. So that tells us a couple things. You can see the Buckminster fullerene is much less stable, it's much higher in energy than graphite, and diamond is also much higher in energy than graphite. This tells us that all the carbon in the universe is slowly being converted to graphite. So all of the diamonds out there and the little bit of Buckminster fullerene that's out there will all inevitably at the end be graphite. Okay, so when we think about this definition, again, the formation of 1 mole of a substance from elements in their standard state, so we can look at a sample equation. So imagine we wanted to figure out the enthalpy of formation of methane. So this is methane, so the reaction that we would draw would be carbon in the graphite form plus hydrogen gas, that's the standard state of hydrogen, bringing those together to form CH4, our methane gas. So the standard state of graphite is 0. The standard state of hydrogen gas, the enthalpy of formation are 0 for both of these. If we were to look up the delta H of formation of methane in an appendix, we'd find out that it's negative 74.8 kilojoules per mole. So if we were to run this chemical reaction and react graphite with hydrogen to form methane, the enthalpy change of the reaction, delta H of reaction, right? This is a state function. So in order to find this, all we need to know is the final state of enthalpy minus the initial state of enthalpy. So from our reaction, this is really the enthalpy of the products minus the enthalpy of our reactants, which in this case would be negative 74.8, that would be the products, minus 0 for the reactants. So delta H of the reaction would be negative 78.4 kilojoules per mole. This would be an exothermic reaction because of that negative sign there. So let's look at an example and go through this in a little bit more detail of how we can solve these problems. So let's imagine we're looking at this acid-base neutralization reaction. So HCl plus sodium hydroxide goes to sodium chloride and water, and this is going to produce heat as well. And what we want to determine is how much heat will this reaction produce. So a couple things to remember. The first thing we can remember is that the change in enthalpy is equal to the heat flow at constant pressure. All right. And the second thing to remember is delta H is a state function. So if we know the initial and final enthalpy amounts, we can determine the total change. Another way of putting that is if we know the enthalpy of formation of the products and subtract the enthalpy of formation of our reactants, we can find delta H of reaction. So let's see what that looks like. Here's the same problem. Here's our balanced chemical reaction. We can then turn to an appendix, either in the back of the book or online, and look up these delta H of formation values. We're going to look it up for everything in our reaction, paying very careful attention to the phase of matter of each. So here's a sample table, and notice there's two versions of water on this table, water as a liquid, water as a gas, and these water as a liquid, water as a gas have different enthalpy of formation values. So it's very important that we pay attention to the phase of matter in our chemical equation. What we're then going to do is the delta H of reaction, right, is going to be equal to the final minus initial, which is the same thing as saying is going to be equal to the sum, so this symbol means sum, of all of the heats of formation of the products minus the sum of all of the heats of formation of our reactants. So when we think about this, we can start off with the products. And so we're going to look up sodium chloride aqueous. You can see it has a heat of formation of negative 407.3. Water as a liquid has a heat of formation of negative 285.8. Right? So if we solve that out, we would have the sum of the products would be negative 285.8 plus negative 403.3 equals negative 693.1 kilojoules per mole. Really easy to lose your negative signs in this, so please be very careful. These are both negative values, so we're going to end up with a bigger negative. We're going to do the same thing for our reactants now. We're going to look up sodium hydroxide and HCl. And if we do that, we see HCl is negative 167.2. And then we're going to add to that our negative 470.2 for sodium hydroxide. And we get negative 637.4 kilojoules per mole. So now what we want to do is just subtract these. So we'll take the negative 693.1 and we're going to subtract a negative 637.4. Again, watch your negative signs. Negative 693.1 minus negative 637.4 equals negative 55.7 kilojoules per mole. So this is the heat of reaction for our neutralization reaction of sodium chloride and HCl. That is the amount of heat that will be released for this chemical reaction, for each mole of this chemical reaction. One more thing I should mention is when you're calculating the heats of the heat of formation, the delta H of your products and reactants, pay attention to your stoichiometric coefficients. In this case, everything was 1 to 1. If, however, we had 2 HCl's, we would need to multiply that 2 HCl's by 2 here. So whatever your coefficient is up here, you're going to have to multiply by the same coefficient down here. We can then use that value we just calculated to start to answer more questions, and questions that we've already seen. We just have a new entry point into them. For example, we can now say calculate delta H of reaction when 0.05 moles of HCl is mixed with 0.05 moles of sodium hydroxide. So what will the delta H of this reaction be? Well, when you think about this problem, it starts exactly the same as what we just did. What we're going to start to do is start to look up heats of formation. We will then find delta H of the products, delta H of the reactants, subtract them to get our answer of negative 55.7 kilojoules per mole. So this is the heat change, the heat released, because it's negative per mole. But since we're dealing with only 0.05 moles, we're going to take that into account by taking our 0.05 moles of reaction and multiplying it by our conversion factor, negative 55.7 kilojoules per mole, and we get negative 2790 joules. So this is the amount of heat that's released if 0.05 moles of HCl were to react. We could even take this a step further and ask the question, if this same chemical reaction was performed in 100 milliliters of water in a coffee cup calorimeter, what will the change in temperature be? So again, this is what allows us to predict what will the change in temperature be. And if we think about this, we've solved similar problems like this before. And so we can take the pieces that we need, so it's the same chemical reaction, and we know what the overall Q or delta H is for this. We remember our coffee cup calorimeter. So the last things we have to remember are delta H is equal to the heat flow at constant pressure. We know Q of the system is equal to negative Q of the surroundings, right? So it's the equal magnitude, opposite sign. And we know Q is equal to MC delta T. The specific heat of water is 4.18 joules per degree Celsius per gram. And so we can go ahead and calculate this, and we see that 2790 joules equals 4.18 joules per degree Celsius per gram times 100 grams times delta T. So if we solve for delta T, we find that the solution will have a delta T of 6.67 degrees Celsius, right? So this is an exothermic reaction. So our water temperature will go up, and it will go up by 6.67 degrees. Thank you.